Back in February, I took a trip with the OSU Astronomy and Physics clubs to Green Bank, West Virginia. And now I present to you the Green Bank Observatory. The Green Bank Observatory is home to 9 radio telescopes. And of course, one of those scopes is the Green Bank Telescope, or GBT for short. It is the world's largest fully steerable radio telescope. It is stankin' big. What is radio astronomy? We study the universe mainly by observing the electromagnetic radiation it emits, and we have built instruments to detect signals all across this EM spectrum. Radio astronomy is simply the study of EM signals on the low end of the spectrum, around 100 MHz to 100 GHz. Within the radio spectrum, there are an abundance of phenomena to observe, such as hydrogen's H1 transition, pulsars, which are neutron stars that spin really fast, and due to their fixed off-axis field, emit pulses of radiation we can detect. And of course, some are trying to find signals of extraterrestrial life. The basic instrument to radio astronomy is quite simple. Even your satellite TV dish qualifies as a radio telescope, only it's tuned to receive radio waves from satellites in Earth orbit, not cool stuff in space. A radio telescope is a fancy satellite dish. EM waves are focused down into a feed horn and onto an expensive antenna. The signal is then mixed with a local oscillator close to the frequency you want to detect, and the lower frequency beating from the now interfering signals is filtered, amplified, and sampled. Thus, extremely high spatial resolution and sensitivity are features of advanced radio telescopes. We got to play with the 40-foot telescope that Green Bank maintains for visitors. Underground, below the scope, is a control room in which one can aim the scope and collect data. Those are the controls from the 70s. Simply, the signal from the antenna is mixed with a local oscillator, and the amplitude of the beat frequency is measured. We took signatures of the H1 transition in the Milky Way. After aiming the scope at a known object, we scanned the local oscillator around the frequency we want to interrogate, which for the transition is 1.4 GHz, and we measured the amplitude of the beating at each point. In doing this, we're essentially visualizing the spectrum in the frequency domain, or what one would call doing a slow Fourier transform of otherwise broadband EM signals from our antenna. We then print the data with a seismograph thingy-majigger. Grace and her very own H1 signature. Notice the large peak, which is the bulk of the H1 emission, but also some smaller peaks to the left and right. These correspond to red and blue shifted H1 emission radiation due to the rotation or motion of the thing that you pointed the scope at. Now for the real presentation, the Green Bank Telescope. As you may have guessed, these pictures are taken with film cameras because digital devices are not allowed a certain proximity from the scope, as even their seemingly minuscule EM signature could be picked up by the sensitive detectors on the GBT. Green Bank has to sometimes bug the locals even to turn off an appliance because it's emitting too much noise. The dish is 100 meters in diameter and 500 feet tall. Each of the 4,000 subreflectors can be individually articulated to 1,000th of an inch precision, and a laser array is used to realign these reflectors. Special $80 per gallon paint must be used on the reflectors to absorb IR radiation. Otherwise, IR would be focused down into the feed horn and the instrument would get cooked. The telescope can resolve about 1 arc second, which is equivalent to viewing the area of a quarter from 3 miles away. We also got to tour the control room for the GBT. it was explained that scientists from all over the world can reserve time on the scope, but of course not without bringing their purse along, or grant. Green Bank is, after all, a $100 million a year operation. It is also being defunded by the NSF and is seeking funding from outside sources, such as a gravity wave project called NanoGrav and a search for ET intelligence project called Breakthrough Listen. And actually, 25% of the scope's time is currently being used by Breakthrough Listen founder and Russian billionaire Yuri Milner to search for aliens. Though Green Bank's future is perhaps uncertain, one thing is for sure. It is projects like these that continually inspire me, and other scientists I'm sure, to design the craziest experiments and build the impossible so that we can uncover the unimaginable.